Okay, so we have the first question here. The question says, I have to sketch the circuit for a single phase half wave uncontrolled rectifier feeding a resistive load, labeling all the components. So we need to sketch what? A single phase half wave uncontrolled rectifier. So you know that uncontrolled rectifier is a rectifier that contains a diode. Okay? Controlled rectifier contains what? A thyristor, not so. So it's a single phase half wave, right? So just a half wave rectifier, the one we know, with one diode in series with a load. Okay. So let's draw that circuit. Okay. That's all we want. So solutions. Okay. So this it's uncontrolled rectifier. We need to have a diode, right? Okay. Okay. So this diode have a load here. And they said it's a resistive load, right? So I'm feeding a resistive load. So we have a resistive load here. Okay, and then we have the source here. Remember that the rectifier converts the AC voltage to DC, right? So the source is AC. Okay, so this is source, AC source, right? Okay, and then that's all we want. Okay, so this is the load. This is a resistive load. So I'll call this RL. This is a diode. Okay, this is a diode. And we have AC source here. Okay, so this is called the source, right? Okay, so that's all we want, right, from question number A. So we want this is single phase half wave rectifier. Okay, that's all. So sketch a circuit. That's a circuit to sketch, right? And then part B says assuming the half wave rectifier circuit sketch has a resistive load of 25 ohms, right? So we are told now that okay, oh, this RL is 25 ohms and 50 hertz AC voltage source. So okay, this voltage source, this supply is 50 hertz. And this voltage supply has RMS voltage of 110, okay, volts. And there is no voltage drop across the semiconductor diode. So we're assuming that, okay, this diode is ideal. So there is no voltage drop across this, okay. Calculate the converter efficiency with the given parameters, okay. So I want to find the rectification efficiency here. That's what we find. How efficient this one is. Okay, so let me just list the data given. So we are given the load. Okay, so we're given the resistive load, RL. RL is given to us as 25 ohms. We are given the frequency. Okay, we're given, okay, the supply frequency is 50 hertz. What else are given? Oh, we're also given the supply, the source RMS, right? RMS voltage. Oh, we are given this is as 110 volts. Okay, so what else are given? I think that's all. Yeah, we're only given those, that data. So the first question, oh, we have to find the efficiency. Okay, rectification efficiency. So efficiency, okay, so rectification efficiency is equal to the ratio of the output DC power divided by the output AC power, right? Okay, so DC power divided by AC power. Okay, so this DC power is simply can be calculated as well the product of DC current times DC voltage, which is average DC. So this is average DC current, average DC voltage. And then AC component, this one can be calculated as what? The product of RMS current times RMS voltage. Okay. Oh, if you have this data, you have all this information, you can calculate. But what if you just have one of those, right? So you can also, oh, you know that power is simple, same as I squared R. So this one will be what? I DC squared, the same thing, times the resistor, which is the load. So this is RL in this case. And then divided by I Ri minus squared. So I'm just giving you different forms of this equation, okay? Times the resistor is the same RL load. Oh, sometimes also we can also write this as what? V squared DC, right? V squared over R. Okay, so you notice that this RA and RA will cancel out. Okay, these guys can cancel out. So you can also find the efficiency by just having the DC current squared over the RMS current squared. Okay. This is also the same case. You can also, remember that power is also same as V squared over R, right? So this is VDC squared over R divided by V RMS squared over R. This RMS I'm talking about is the output RMS voltage, okay? Not input. Divided by R. And if you R and R cancels out, you're going to have VDC squared over VAC squared or VRMS squared. So you can use any of these to find the efficiency. Okay, now from the given data, how do we find those parameters, right? So you can find VDC. Okay, you need to understand that for a half-wave rectifier, has got the following waveform, right? Okay, this is a time. This is a voltage, right? So you notice that, so from half a period, which is pi, 2 pi. Okay, so you have the input voltage. I'll label this in blue. Okay, so the input voltage, I'll just take it for one time period. Looks like that. And then the output voltage is that it cuts off the negative cycles, right? So the output voltage will end up looking like this, right? Okay, or during the negative cycle, it will be off. And then it will come on like that also during the other period, and then to be off. Okay, so if you notice, the total time period for this one, it's 2 pi, right? That's the total time period. So period is equal to 2 pi. Okay, you notice that if from here, during the other half period, it's off, and then it continues just like that, right? Okay. Okay, so this is a supply voltage. It's a 3 pi. If I continue drawing like that, this is how it's going to look, right? Okay, but if you look at the output voltage, it's a different story, right? So this is the output voltage. Or this is VO. Okay, or this one is VS. Okay, so you see that, okay, half the cycle it's on, half the cycle it's off, right? So you can find the average voltage for that. And this average voltage is equal to, so it's called a VDC. So VDC is simply equal to 1 over time period, which is 2 pi, integrating from 0. You see that that waveform was on from 0 to pi, okay? And then from pi to pi, it was off, right? So you're integrating from 0 to pi. And then the sinusoid, right, voltage, omega t with respect to omega t. And if you integrate this, I'm not going to do the integration and all that, you end up having a Vm over pi. Okay, so this is a DC voltage, where this Vm is a peak input voltage. Okay, so this Vm is simply the square root of 2 by the RMS voltage, the input RMS voltage. This RMS I'm talking about is the input, okay, and then divided by pi. Okay, so the peak voltage is simply the square root of 2 times the RMS voltage. Okay, so from this, we can find the DC voltage, right? So you can find the VDC. Okay, it's very simple. Since we have the data already of the RMS voltage. Okay, so just multiply by √2, divide by pi, you have the VDC. Okay, what of the RMS output voltage? Okay, how can you find the RMS output voltage? So the RMS output voltage, I'll call this V output RMS. Oh, in fact, this one is the one we're supposed to use when finding the efficiency. Okay, so this is equal to 1/2 pi, the same formula, right? Okay, integrating from 0 to pi. Okay, Vm sine omega t squared, right? Okay, it's mean square, right? You have to square this function, and then the omega t. Okay, root mean, so you need the square root, right? It's a root, so to the power 1/2. So this is square root. Okay, and please, do the integration here. I'm not going to do the tedious integration here, but just know that, okay, this one becomes what? It's a square right inside there. So you have 1/2 pi. Who doesn't know how to show this integration here? So I'm going to have v squared m sine squared omega t, because we are squaring that, the omega t. Okay, don't forget that at the end you have to put in the square root, right? So this is square root I'm writing here. So you see that the V output RMS only becomes what? Oh, so if you try to integrate this one, this sine squared omega t, this is can be replaced by half 1 minus cos omega t. Okay, if you want to integrate that. Okay, so try to replace that with the half 1 minus cos omega t, do the integration. This just comes out to be Vm/2. Okay, so this is the RMS output RMS voltage for
Waivala ko tum simwene kelongala tum cos 2 Wt.
Oh yeah, this is cos 2 omega t, yes, correct. It's 2 omega t, yes. Okay, so if you integrate that, you substitute the limits, you'll be able to get Vm/2. This is for single phase half wave rectifier. This is how you get the output RMS. Just divide the peak voltage divided by 2. Okay, so this is the RMS voltage. This is the output RMS voltage. Now let's go back and now find the parameters that we need, right? Okay, so from there now we can therefore say, okay, VDC. So we have the formulas here. So VDC is simply equal to, okay, we found this to be Vm/what? Pi, right? And since we're not given Vm, we're given RMS instead, so we can find it. The Vm just multiplied by the RMS voltage, which is given times √2. Okay, and then divide by pi. And this is equal to the square root of 2 multiplied by 110 divided by pi. Okay, so how much is that? How much is that? Okay, I do not have my calculator, but I can use my phone, I think. 110 times √2 divided by pi, right? Okay, so this is giving me about 49.5, right? 52 volts. Okay, so this is the output DC voltage, the average, right? So now since we have the DC voltage, the output, you can find the DC current. Okay, so we can also find the output DC current. So IDC is simply equal to VDC divided by resistor, which is RL. Okay, so what is VDC? VDC is simply what? √2 times VRMS divided by RL. This is over pi also, so you can say RL times pi, right? The same thing. Okay, so if, we already found this VDC, the order of that, which is for 9.52. The only thing you need to do is just divide this guy by the resistor, right? So the resistor was what? 25 ohms. Okay, so that value divided by 25, this is 1.98. So the output DC current is simply 1.98 amps. Okay. Oh, now we can find the RMS. So V RMS, also we need it. V output RMS. So this is output RMS voltage. This is equal to, remember that we I just shown you how to do this, just Vm divided by 2. Okay, so Vm. Okay, so what is Vm? Vm is simply equal to, okay, this Vm is simply the peak voltage, right? The input peak voltage, and we don't have the input peak voltage. Instead, we have the RMS of multiplied by RMS, right? Okay, so root 2 by 110 divided by 2. Okay, so if we multiply that, we have root 2 by 110, okay, divided by 2, we are getting 77.78 volts. Okay, so that's the output RMS voltage. Okay, now we can also find the output RMS current. So we can say IO RMS. This is equal to VO RMS divided by the resistor given. So the resistor is 25. The output RMS voltage we are given, we found is 77.78. The resistor is 25, right? Okay, so 25 ohms. Okay, so if you divide the two, you get the output RMS current as 3.11 amps. Oh, I think now I have everything now at disposal, right? Yes, we have everything. We can therefore do what? Find the efficiency. So the efficiency, I told you there are so many options you can use there, the answers to be the same, right? Okay, you can use the power, output power, over input power. Anyway, let's use the output power. Output DC power divided by output AC power, right? Okay, so this will be equal to VDC times I DC divided by, but you can also try the other one, I squared DC over RMS squared. It is to give you the same efficiency, okay? But I just want to have in terms of power. Okay, so this is the V output RMS times I RMS, I output RMS. Okay, so VDC RMS, VDC was what? 49.0. Oh, how much was it? 49.52. IDC was 1.98. Okay, and then here we have 77.78 times 3.11. So I can multiply by 100% because I want to get my efficiency in percentage. Okay, so for 9.52 times 1.98 divided by 77.78 times 3.11. Okay, so this give me about 40.5%. Okay, so this is rectification efficiency. So how much this one is rectifying from converting from DC to AC. That's how much conversion is there. So about the 59.5% is still not converted. It's a ripple, in short. Too much ripple, right? Okay. So that is the rectification efficiency. Okay, that's part A. And then we go to part 2. Says an assumption that the source has a resistance of 60 ohm in addition to the gain parameter. No, this time around, oh, okay, this source has got some resistance in it, which is 60 ohms. What effect is going to have in terms of efficiency? Will the efficiency be the same in terms of power, or power output be the same? Let's see. Okay, so now that source, we're going to represent it, we're going to replace it with what? We're going to add a resistor in series with it. Okay, so we have the source here. In series with a source, I'm going to add a resistor of 60 ohms. Okay, and then the rest still follows, right? But without, of this load resistor. Okay, this is RL. And then this is RR source from the source, right? Okay. This is a diode. So this RR source is 60 ohms. This is 25 ohms. So we repeat the same procedure. Let's find out how would the efficiency of this be. Okay. Okay, we continue. So what do you think will happen now? Anyone with an idea? Okay, so we can also repeat the same thing. Let us find the current now. Since now we increase the resistance in our circuit, the current in the circuit will reduce, not so. Okay, that's a fact. So if the current reduces, while all the parameters are still the same, what happened to the power? Okay, the power actually also reduced, not so. Let's see. Okay, so with that information, since the output DC voltage used to be the same, okay, remember this formula here, it doesn't change. There's nothing to do with the resistor here, this integration here, right? The one we found, okay, oh, the output DC voltage is simply Vm over pi, or this one here. You notice that we still have the same parameters, right? The RMS input voltage is still the same 110. So it means that even the output DC voltage will still be the same. It has nothing to do with what? Oh, it has nothing to do with the resistance that we've added. Okay, so we can go ahead and find now the current, right? Okay, so the current, you're going to use this formula here. The IDC current, so we're going to have VDC divided by R, isn't it? Okay. Now this time around, this resistor, what would be the value of this resistor here? Anyone have an idea? How are we going to find that resistor? Which resistor now are we referring to? Okay, let's move. People are not responding. Okay, so
Which resistance? Which resistance are we referring to? Or you mean the total series resistance?
Yeah.
We are supposed to add 60 and 25.
No, you're not saying anything. So with the inclusion of 60 ohm, okay, of 60 ohm source resistor.
Sorry, I was on mute.
Source resistor. Okay, so the total resistance increases, right? So this total resistance is going to increase. So R total, therefore, we go to RL plus RS, which is equal to 25 plus 60, so 85 ohms. So this is going to limit the current. So this is going to limit the current, right? Limit the current. Okay. So let's see now, what will be this new IDC current? So the VDC is still the same. So now this will be the R total. So the VDC is for 9.5 watt. What was that? For 9.52. Divided by R total. R total is now 85 ohms, right? Okay, so let's see. So for 9.52 divided by 85, we have current now in the circuit equal to 0.583. Okay, similarly, let's look at the IRMS current, right? So what will be the IRMS current? The RMS voltage is to be the same. So IRMS will be equal to VRMS divided by the R total. So even the IRMS volt current is going to reduce. The VRMS was 77.78. And then divide by what? R total, which is 85, right? Okay, so 77.78 divided by 85, you have 0.915 amps. So this is RMS. Now we can find the new efficiency, right? Okay. So the new efficiency now becomes what? So you can say VDC times IDC divided by VRMS times IRMS. So this RMS is actually the output, right? Okay, this one I'm referring to. Okay, so this is equal to 49. Okay, just a minute. Okay, so I'm going to use this. Okay, so this also can be written as IDC squared times RR. I have to use this formula, let's see, over IRMS squared times R. So I want to use the other one now. So you notice that IDC is 0.583 squared times R. So what is R? R is simply equal to what? 25. So you notice that these guys will cancel out, right? And then IRM is 0.915 squared times 25, right? Okay. So if you do that, you see that even the power, let me just get those in terms of power. Let's see, 0.5883 squared times 25 squared. So I have 8.492 here, 97 watts. Okay, here I'm getting what? 0.915 squared times 25, 20.93. But if you look at the efficiency, it's still the same. Has it changed? No. Times 100%, the efficiency will be the same, right? Let's see, 8.49 or whatever there, divided by 20.93. The efficiency will be still the same, right? Which is 40.5%. So even if you add more load, okay, the resistance, the efficiency will be the same. And the only thing that is going to reduce just the current in the circuit. Okay. Any question? People, what's wrong? Why are you quiet? No one is saying anything. I don't know if whether we're moving forward or backwards. No one is just saying anything, just quiet.
All good, all good. We are following.
Want a class, they can't say anything.
Can't see and I'm a mic on.
Anyway, let's move. So now the question says we have to draw the circuit in above, but this time around we are with a resistive inductive load and a freewheeling diode connected across the load. Then we have to find the output waveforms. Okay. Let us see. So now we have in addition to the resistive load, we have an inductive load added to it. Okay. So this is question C. Okay, so question C says, oh, okay, we have an RL load. Okay. An RL load waveform, right? So I have to sketch this waveform. Okay, so what we have, okay, is this. Say source, right? What we diode here. And then we have an inductor. And we also have a resistor. It's an RL load. Okay, this is R, this is L. Now I want to see the behavior of this, right? Okay, so we're getting the output from here. It's the output voltage we're collecting here. Okay, so this is source voltage also, and then you have a diode here. Now allow me to draw this here. Okay. In fact, let me just do this. Okay. So now I'm going to draw. Oh, I also have to put a freewheeling diode. Okay, I forgot that. So here's a freewheeling diode. It's connected parallel to the load. So I have a freewheeling diode. This freewheeling diode is connected parallel to the load. So this is DFW, freewheeling diode. Okay. Now let's draw the waveform.
Almost looking as though it's a converter circuit.
Yeah. Yes, it's okay. So it can be a converter. It's actually
Back booster.
DC to AC. Oh, sorry, AC to DC.
Oh yeah.
Okay. So I'm going to have the output across the load. So I'm going to have three waveforms, or about four. Let's see. Okay, so the first one is going to be the input. Okay, so this one will be the input waveform. The next one will be the output waveform I'm going to draw. Okay, the other waveform I'm going to include okay, let me see the voltage across the freewheeling diode. Let's see how it's going to look. Okay, and what else? So I can say, okay, out of the voltage across the diode, the rectifier diode, right? Let me see also how it's going to look. Okay. Okay, so this axis is the axis for voltage only. Okay, it's the voltage axis. So the first one, like I said, okay, so let me just say, okay, we have this is a half period, which is pi. How many boxes? 1, 2, 3, 4, 5, 6, 7 boxes. Again, 7, 1, 2, 3, 4, 5, 6, 7 boxes. This is 2 pi here. One, 2, 3, 4, 5, 6, 7. This is 3 pi. One, 2, 3, 4, 5, 6, 7, 4 pi, and so on and so forth, right? Okay. Now, let me just now put the out input. Okay, so this is the input voltage. Okay, so this is the input. Oh, sorry. Okay. Okay, so we just, okay, to continue, but I just decided to draw for just 2 time period, right? Okay, now, you know that what will happen is that, okay, just a minute. What's that noise? Okay, so the output, know that a diode is going to block this part of the voltage, right? The negative part of the voltage, right? This one we blocked, isn't it? We know that it only allow this positive cycle. Okay, so what's going to happen is this. So since there's an inductor, okay, so since there's an inductor, you need to understand that the output voltage, okay, the output voltage, let me just, so not body, but the current, let me just, why is this not working properly? Okay. So it's going to block the positive cycle, okay? So these are the same phase. Okay, so you notice that even for the next cycle, so to only allow the positive cycle to pass, right? So again, leaving this one, just be like that, okay? And then after here again, if this guy continued, you're going to have the same behavior, right? So on and so forth, isn't it? Okay, now I think I need to include the current here. So I'll show you the behavior of the current, right? Okay, so let's say this is the current output, or the current through the rod. So IO, right? So what will happen is that the current doesn't just change abruptly in an inductor, right? Okay, it's going to slowly increase. Okay, slowly increase, and then when this is maximum, okay, so let's say this is the maximum point of the voltage, right? That's the maximum point of the voltage. At that point, the current will start reducing also after it reaches the maximum. So to start first increasing, that's the behavior when there's an inductor, and then here it will decrease like that. It won't just go to zero at this point, right? Okay, so it will decrease if the inductor is large enough, and that this during this whole period when the diode is off, there'll be current in the circuit. Okay, as you can see, there's some current in the circuit here until the next period reaches like that. So this will be the waveform of the output current. So the story starts increasing, and then to reach the maximum here where the voltage is maximum. Okay, and then in fact they don't reach maximum at the same point at the same time. In fact, let me just make this correction. Okay, remember that the current lags behind the voltage, right, in an inductive load. So what will happen is that don't reach maximum at the same point, but the behavior will look like this. Okay, so this now point when this guy reaches the maximum, because the current is lagging behind the voltage, right? And then start decaying. Okay, it decays until the next cycle. If the inductor is large enough, during this whole period it will be decaying. The current will be there, but in a reducing state, right? Okay, so this is during the off period, and this will continue until the next cycle comes also. Okay, the next cycle like that. Okay, and then it continues reducing just like that. So this is how the current is going to look like. Okay. Now let's look at what do you think of the voltage across the the current across the freewheeling diode? Okay, so this current in the along across the freewheeling diode, it will only conduct. Okay, this diode only will be conducting when what? When this diode D, the main diode is off, because during that time the inductor now start discharging its voltage. Okay, it start discharging its current across the road, right? So what will happen is that since this guy is off, the inductor now will have this polarity, positive minus here, so it will still continue delivering the current to the load, right? Okay, so this current will pass through this freewheeling diode like this. So this diode here only conducts when this guy is off. Once this guy comes on, once this guy goes on, what happens that you are going to a positive way minus terminal this side. This diode now becomes what? In reverse bias, isn't it? Okay. Look at this, the cathode of this diode, right? The cathode of this diode is connected to the positive terminal when this guy is positive. Okay, so what happens that there'll be no current that will be flowing through this diode, right? Okay, if the current tries to flow this diode, it will be blocked, and then it to flow through the load. Okay, so this diode flowing diode will only be conducting when this diode D, the rectifier diode, is off. So what will happen now is that the current across the flowing diode to be this current here, this part here. Okay, this part when the diode is off, that main diode is off, this part here is the current that comes as that comes from that passes through the wave freewheeling diode. So what happens that you're just going to have this kind of waveform for the freewheeling diode. Okay, and then it goes off during this time period. Okay, during this time period here it goes off, and then it also comes on at this point. Okay, just like that. So this will be the waveform. Okay, for that current. So this current is the I D freewheeling. Okay, and then you can also scale the waveform. Okay, for the current which is in the load here. I mean, on this main diode here. You notice that this current here is the current ID. If you notice, this current here is the current that conducts when the applied voltage is positive, as you can see, when this guy is positive. This is the current here that you have. Okay, and then this one here, the other side, this current is the one that passes through the following diode. So ID FW. Okay, so these two make up the two currents that we need in the circuit. Okay, and then this is the output voltage, the V output. Okay. Are we together? Hello?
Yes, we are following.
Okay, let's move then. So what's the next question now? So next question says, sketch a circuit showing how a TRIAC can be deployed as a switch controlling power supply to a three-phase AC induction motor. State any one feature of a TRIAC. Okay, so a TRIAC, it conducts in both directions. Okay, and like it's made up. In short, it's made up of what? Two thyristors that are connected in opposite direction. Okay, so it's used to control the AC voltage. This setup where you just have a thyristor like this. Let's say this was thyristor. This one is what? Just only allows forward voltage, isn't it? Forward current. It doesn't allow the reverse. But the TRIAC, the way it behaves like this. Okay, so you have two thyristors. So one thyristor will be connected in this form. Okay. Another thyristor be connected in this form, right? So get the cathode of this guy and the anode of this guy, connect them. Similarly, the cathode of this guy and the anode of the other guy, connect them like this. Okay. And then, okay. So it's a positive supply, it's a negative supply, right? Or since the AC changes. So during the positive side, the positive cycle, okay, it's AC, right? Okay, let me just, you connect these guys to AC source, right? Let me just do this. You connect them to AC source, right? Okay, so this is AC source. Okay, when this side is positive or this side is negative, you notice that when this side is positive, this, let's say this thyristor 1, this thyristor 2, right? thyristor 1 will be forward biased, isn't it? As you can see, thyristor 1 will be forward biased, and as you can see, even its cathode is also negative. Okay, it's connected to the negative terminal. So this thyristor will be forward biased, or this one will be reverse biased. So the current will flow in this direction, right? Okay, the current will flow in this direction, like that. Okay, goes back. But when the terminals flip, the polarity is flip, what happens is that now this thyristor 1 will be off, or thyristor 2 will be on. So the current now will flow in this direction. That's how a TRIAC works. Okay. Now we need to this is a single phase. So for 3-phase, we need to have 3 of these guys. Okay. This is 3-phase source. So we need to have 3 of those thyristors. So how it's going to look now? So we're trying to control what? Control the motor, isn't it? Okay. So let me just go back to the question. The question says, sketch a circuit showing how a TRIAC can be deployed as a switch controlling power supply to a 3-phase AC induction motor. Okay. So now we are going to have a motor. We need to have 3 TRIACs since we have 3-phase. Okay. And also need to have a source, isn't it? We need to have a source. So we need to have a 3-phase source. What question number is this, in fact? This question number D. So question number D. We have a 3-phase source. Okay, so we just draw a 3-phase source, right? I'm going to say this is 3-phase, according to me. So this is a 3-phase source. Okay. Okay, and then to this now we need how many TRIACs? 3. Okay, so this one's going to have its own TRIAC. Okay, this one's going to have its own TRIAC. So with thyristor here, and then here you also have a thyristor. Forgive my handwriting. Okay. Similarly here, also going to have 2 thyristors. Okay. Okay, and then here again, you're going to have another pair. Okay, so this is a 3-phase motor, induction motor. Okay, and then the 3-phase supply here. So 3-phase AC supply. Yeah, just like that. So you know they use. Why am I drawing this as if it's a Zener diode? Anyway, drawing it like a Zener diode, right? Okay, like that. So know the use of that terminal, right? It's one where you supply the gate pulse to turn this thyristor on. Okay, remember it can't turn on minus supplying that gate pulse. Okay, so I have to supply it with a gate pulse, then it's going to turn on. So yeah, that's a simple drawing you can give, right? So this part of the circuit is what the control part of the circuit. This one here. So this is thyristor what? Voltage controller. Okay. So what it happens is that the thyristor can handle both what polarities, positive and negative polarities. So positive, when the polarity is positive applied, you know where it's going to be directed. Okay. So when the polarity is positive, if this polarity is positive, you notice that this thyristor is not in conduction, not so. Okay. So let's say we apply positive, 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 positive. It means that the three thyristors on top are the one that will be in conduction, right? And then apply negative, negative, negative. Okay. You notice that the thyristor, the other three thyristors now, the one will be in conduction. Okay. Any question? Okay, so this is what we have. Okay, change page style. Okay, so a three-phase half-wave controlled rectifier is connected to a 3.3 kV three-phase. Half-controlled rectifier is connected to a 3.3 kV three-phase supply via a delta Y 3.3 kV stroke 0.55 kV transformer. The load of the rectifier is a pure resistive of 5 ohms. The delay angle alpha is equal to 5 degrees. Calculate the rectification efficiency. Okay, so the calculation is still the same, just like the first question. Now that this time around we're dealing with a three-phase. So how do we handle that, right? So the first step is first to find the output DC voltage for three-phase half-wave controlled rectifier. Okay. So part A, let's first list what we are given, right? So we have a star, we have what? Delta Y, right? So on the primary side of a delta, which is 3.3 kV. On the secondary side of star connected is 0.55 kV, right? So we're just focusing on the secondary side because the secondary side is the one that is feeding the rest of the circuit. We're not interested in the 3.3 kV. Okay, we're not interested. You're just interested in this. So this is a line voltage, right? Okay. So I'm given the line voltage of 0.55 kV or 55 volts. So VL is 55 volts. Oh, 550 volts, sorry. Okay, and then we have the load with a resistance of 5 ohms. So R is equal to 5 ohms. Okay. Next, we have the angle. We're given the firing angle, the delay angle, which is 0.5 degrees. Okay, what else? So I have to find now the rectification efficiency. You have to know that the fact that the rectification efficiency is the same, right? Okay, VDC, I'm going to write the same formula times IDC divided by V output RMS times I output RMS. Okay, so from this, we have to find those parameters, right? Okay, so how do you find the VDC for three-phase? So VDC for three-phase half-wave rectifier controlled, of course, it's controlled, means there isn't thyristors. This is given by 1.17, if you want just this one, right? Times V line to neutral. Okay, this is V line to neutral, and then cos alpha. This is the firing angle. Okay, so this is the same as what? If you don't want the simplified one, then this is the √3, 3√2 divided by 2 pi times V line, the line voltage. Okay, so we want to use the line voltage, VL, and then cos alpha. It's the same thing. Okay, so it depends which one you want to use. If you can remember this one, 1.17, but make sure that this one is what? The line to neutral or the phase voltage. Okay, so since we are given the line voltage, you have to convert this line voltage. Okay, according to the rules in three phase, right? So let's find VDC. So if you want to use the first formula here or the second formula, it's okay. I'm going to go with the second one, right? So VDC is simply equal to 3√2 times 2 pi, because the second formula doesn't require me to convert the line voltage to phase, right? So I'll just plug it there. It's 550 times cosine of 25 degrees. Okay, so how much is that? If I put that value in my calculator here, so cos 25, Okay, I'll start with cotton 5 times 550 times 3 times square root of 2, and then divide by the answer by 2, divide by pi. So I have 336, right? So this is 336.585 volts. Okay, so this is a DC voltage, right? Okay, so we have managed to find this, right? Oh, since we have the VDC voltage, you can also find IDC now, okay? So IDC will just be equal to VDC divided by the resistance, right? Okay, so IDC will just equal to VDC divided by the resistor, okay? So VDC we found 336.585. The resistance given is 5 ohms, okay? So 5 ohms there, right? So this is equal to 67.3 amps. Okay, say 32 amps. Okay. Now let's do with the numerator or denominator. So we're done with the numerator. Now let's do with the denominator. So how can you find V or RMS, I or RMS? Okay, so it's trick. So here for output RMS voltage, also it also involves integration, but no, there's just a formula that you can remember, right? So V or RMS for 3-phase half wave controlled rectifier is given by, okay, √2 by the line voltage, and then open brackets 1/6 plus the square root of 3 over 8 pi times cosine of 2 alpha, and then to the power half. This is square root, right? Okay, so this is a V output RMS voltage. So this comes out about after doing the integration, okay, just like we did with a single phase. Okay, so we just have to plug in the values that we have, okay? So V or RMS is equal to the square root of 2. What's the line voltage is 550, okay? 1/6 plus the square root of 3 divided by 8 pi cosine twice alpha. Alpha is 25, so it's cosine 50, right? Okay. The power half. Okay, so let's find out how much that. So we have the square root of 2 times 550, okay, times 1/6 times the square root of 3 over 8 pi times square root of 3 over 8 pi, right? So this is 8 pi times cosine 50, and then to the power 1/2. Oh, okay, a problem here. Okay, this will be plus. So I'm getting a 357, right? Okay, so 357.25 or 2.26, right? So therefore the V output RMS is equal to 357.26 volts. Now with this information, you can find the output RMS current, right? So I or RMS is equal to V or RMS divided by the current, or divided by the resistance, sorry. Okay, so 357.26 divided by 5 ohms. So I have 71.45 amps. Okay, now with this, we have everything we wanted. You can now find the rectification efficiency. So just like I said, you can even use IDC squared over IRMS squared to give you the same answer, or you can use the VDC squared divided by V output RMS squared just to give you the same answer. Okay, but if you want, you can just find the efficiency in terms of power. Okay, so power, therefore, the DC power is simply the DC current times the DC voltage, right? So the DC current here we found 67.32 The DC voltage you found what? Corresponding DC voltage was 336.585. Okay, and then in the numerator, also of IRMS current 71.45 times 357, the VDC with the VRMS times 100%. Okay, so let's count that. So 67.32 times 336.585, and then divide by 71.45 times 357.26. So I have a rectification of about 88.7%. Okay, about 88.7%. So you see, using three phases benefits the half wave. At least the rectification efficiency now has increased, right? So this means that this one has got fewer ripples as compared to the single phase that we looked at earlier. We found 40.5%, you see. Okay, this one was 40.5% single phase. Okay, just with a single diode. But here now have three phase, okay, as you can see. So the ripple quantity or the ripple content has reduced. Okay, so we have more of a DC by that much. So DC output is about 88.7% of the AC input. Okay, so the difference between this, if you subtract from 100%, what you're going to get will be the percentage of the ripples. Okay. Are we together?
Yes, Mr. Steve, we're together.
Okay, so let's continue then. Okay, then we have also to find the PIV of a thyristor. Who understands what a PIV means? Who remembers? Okay, so PIV means the peak inverse voltage, right? So that's a voltage that a diode can withstand, okay, in reverse bias. Remember that when the diode is reverse biased, the whole source voltage appears across the diode. Okay, when the diode is reverse biased, it means that it has to withstand the whole source voltage, the peak voltage from the source, that withstand that. Okay, or else if it doesn't withstand that, the diode will be destroyed. So what I'm trying to say here is this: consider this case here. If you have let's say you have a diode here, okay, this is a diode, this is a source, and then this is the load, right? During a positive cycle, this diode conducts, right? Okay, but now during the negative cycle, do you see what happens? Let me show you what happens. During the negative cycle, when the terminal here is negative, here is positive, what happens that this diode will be off, right? Won't be reverse biased. So to act as an open circuit. So this side there'll be no current flowing through it, no current at all. Okay, so it means that this voltage here, the source voltage, okay, if you apply KVL here, this source voltage will be equal to the voltage that is going to appear across the terminals of the diode here. Okay, so this will be negative Vs. Okay, so the whole of this voltage here is going to appear across the diode when this guy is in reverse bias. Okay, but when it's in forward bias, then this guy behaves like a short circuit. Okay, just behave like a short circuit, right? But the real diode doesn't behave like a short circuit. This does a very small voltage drop of about 1.7 volts if it's a silicon diode, isn't it? But when it's in reverse bias, the voltage that is going to appear across it, it's what? The equal to the source voltage. And that voltage is called peak inverse voltage. Okay? It has to, what should be the rating of the diode itself, right? So it has to be at least 5, or at least the value of voltage source, Vs. Or else if the rating, for example, voltage source is 50 volts, and then the rating of this diode is 40 volts, then this diode is not suitable for this circuit, because during the reverse bias, what's going to appear across the terminals of the diode will be 50 volts, but it can only withstand 40 volts. So this diode will be destroyed. So it needs to have a rating of at least 50 volts. 50. Okay, so the rating of that diode should be greater or equal to 50 volts. Okay. So depending on the use of the diode, where to be used, the source voltage, the rating also has to be good enough. Otherwise, if you choose a diode that has smaller peak inverse voltage, you end up destroying the circuit. Okay, so in this case, if you notice here, the rating of the diode, the peak inverse voltage of the diode, then it's just going to be the peak voltage of the source, right? Okay, and what is the peak voltage of the source? Remember that these guys here. Okay, let me just correct you, sir. This voltages here are RMS voltages always. Okay, this if you say given okay 250 volts source and all that, it's just mentioned like that. Just know that those are RMS voltages. Okay, so we have to find the peak voltage. So the peak voltage is simply the square root of 2 times the RMS voltage. Okay, so the peak inverse voltage is equal to the square root of 2 by the RMS voltage. Okay, so this is the peak. Remember, if it's been saying that peak inverse, right? It's peak voltage. So we have to multiply by square root of 2 if you are given the RMS voltage. So this will be root 2 by 550. Okay, so that will be the peak inverse voltage. Okay, so about 777.8 volts. So meaning this diode shouldn't have a rating of less than this. Okay, so in this case now, question here, it means that we can't have a diode that has a rating of 500 volts. Okay, it can't work in this case. It has to be something greater than this, right? Equal or greater than this. Okay. Okay, so let us go to question number B. Question number B says a chopper circuit is operating on a TRIAC at a frequency of 2 kilohertz on a 550 volt supply. You know what a chopper does, right? It's a DC-DC converter, right? So that's the first understanding we need to have. A chopper is a DC-DC converter. It either steps down the DC voltage or steps up the DC voltage. So if the load voltage is 400 volts, calculate the conduction period of the thyristor in each cycle. So yes, now looking at the problem that we have here, we have the supply of 550 volts, right? And the load voltage is 400 volts. What kind of a chopper is this?
It's a step down chopper.
Step down chopper, right? And that is what we call a biconverter, isn't it? Okay, so we have a biconverter here, step down chopper. So we have to know the relationship between the input voltage and the output voltage for what? A step down chopper. So I didn't mention to us that this one step down chopper or something. Looking at the figures that are given here, must be able to tell, okay, this chopper is this kind of a chopper. Okay, so we have the source is higher than the output. So we have a step down chopper, and the step down chopper is called what? A biconverter. Okay. So let's go to question B. We see what we can do there. So question B, we are given the data here. We are given the supply voltage. The supply voltage is simply 550 volts. Okay, the output voltage. So of course this VO. VO is given as 400 volts. And you're also given the frequency. The frequency is actually the frequency, the switching frequency. Remember that in a chopper there is a switch, right? And that switch is what? Either MOSFET, okay, or maybe BJT, but BJTs are not commonly used, or IGBT, okay? So we're given that, okay, we're switching that switch at a frequency of 2 kilohertz. Okay, now I want to find it. So the question says we have to determine the time, okay? Calculate the conduction period of the thyristor in each cycle. In each cycle. So I want to find out, okay, during this cycle when it was on, what was the conduction period? How long was this thyristor on, or how long was it off? Okay, so now the first thing we need to determine first the relationship between what? So we have a biconverter, as I mentioned. It's a biconverter. Okay, it's a biconverter. Okay, we know that fact. Looking at the data given here, it's a buck converter. And since the buck converter, we know that the output voltage is equal to the supply voltage times the duty cycle. This relationship that we know for buck converter, step down chopper. And we know that duty cycle, by definition, is a ratio between what? The on period of that cycle divided by the total period. That's the dimension of what? A duty cycle. Total time period. Okay. So I can replace this with symbols. I can say, okay, T on divided by total time period. Total time period consists of what? T on plus T off. Plus T off. Okay. And the T on plus T off is simply the total time period, right? Which is T. So this is a duty cycle definition. T on over T. That's a duty cycle definition, right? What do I mean on and off? On and off, let's say of what? This is a pulse that we are giving to the what? To the circuit. It's a pulse. This is a pulse, right? So on period, it means this is a period when from here to here, that's the on period. This is the on period. From here to here, it's the off period, right? And as you can see here, from on up to off, this whole period is called total time period. Okay, so the duty cycle is simply the ratio of the on period divided by the total time period. So it tells you what fraction of the period is the what the signal on, in short. Okay, that's a duty cycle. The higher the duty cycle, it tells you that okay, there is a long time period when the signal is on, as compared to when it's off. So if you say it's a 50% duty cycle, it means that it's more like what? A half wave rectifier, right? You can look at it like a half wave rectifier. It's a 50% cycle, 50% duty cycle. It means that during half the period is on, half the period is off, half the period is on, so the period is up to here, right? So this guy here, as you can see, this one has 50% duty cycle. On period here, this is off period. Okay, so that's a main idea behind the duty cycle. So you can, so now you can replace, in place of D, now you can put what? T on over total time period, right? So we have the equation now. Equation looks like this. So VO is equal to VS times T on over T. So we have T. We can find T. We have VS of VO. We don't know T on. So we have to find the total time when it was on. Once you know the time when it was on, you can also find the time when it was off, right? Okay. So this is the VO over VS times T. So you can find the total time period when it was on. Okay. Now what is T? Remember that T is equal to 1 over frequency. So we are given the frequency, which is 2 kilohertz. Huh? So 1 over 2 kilohertz. So kilo is simply 1000. And if you take this 10, it means 10 to the power 3, right? If you take it on top, it becomes half millisecond, right? Half positive. Kilo becomes milli, right? It's in the denominator, right? So this is half millisecond, or you can say 0.5 milliseconds. Okay, so this is a period, isn't it? Okay, so now we can find now what time, how long was it on, right? Okay, so VO is 400. Okay, VS is what? 550. The time period is simply 0.5 milliseconds, right? Okay, so let's multiply the two. So 400 over 550 times 0.5, you see that here we have 0.364 milliseconds. 0.364 milliseconds. It was on. Okay, and then you know that time period is simply the sum of what? the on period plus the off period, isn't it? That's the time period, right? T off. So you can find the T off at this point also. So if you solve this, you find that T off. Okay, so T off will be equal to total time period is T minus T on. So this will be 0.5 minus 0.364. Okay, so this is how much? So 0.5 minus that, you're getting 0.136. That is T off. Milliseconds. So if you want now, you can even find the duty cycle. So duty cycle, you can also find, right? Which is it? T on over T. So in case the question asks you, find the duty cycle for this, you now find, right? T on over 2 time period, right? So T on is 0.5, or so 0.364. The duty cycle, the total time period is 0.5. So you can find the duty cycle from there, I think. So you have 0.364 divided by 0.5. So 0.728, right? 0.728. Or in simpler terms, this is 72.8%. This was on for that time period of 72.8%, right? It was on. 100% duty cycle means that it's on throughout, and that is maybe, I don't know if that's the case. There's something like that. That's not a power percent. 100% duty cycle means on throughout, right? So 72.8% is the duty cycle. In case the question asks you, okay, find the duty cycle for this. Yes. So this I can do the calculations here. Any question? Any question, please? People are quiet. They can neither confirm nor what.
No question.
Why are you quiet? Class becomes boring and everyone is quiet. Okay, so that's what we can do here. Let's look at the next question. So the next question says a DC chopper has a resistive load of 20 ohms and an input voltage of, so I given the input voltage. When the chopper is on, its voltage drop is 1.5 volts and the chopping frequency is 10 kilohertz. If the duty cycle is 80%, determine the average output voltage and the chopper on time. Okay, so here we have two questions. We have to find the output voltage, okay, which is VO, and also we also need to find the time when the what was on, okay, the signal was on, the input signal, okay. So we need to find out what was the output. From there, we're going to conclude whether this chopper, is it a step up or step down, okay. Let's see first. Let's find out. So a DC chopper has a resistive load of that and the input voltage of that, right? The chopper is on. When the chopper is on, its drop is 1.5 volts and the chopping frequency is 10 kilohertz. So we're told the duty cycle is 80%. That means the average output voltage and the chopper on time. Okay, so we are given the duty cycle already, which is good. So we don't need to stress, right? We're given the duty cycle already, which is okay. Okay, so we move on. Let us move on. Okay, so let's list what we are given. We are given the source voltage. So given the source voltage here, the source voltage is 220 volts. Okay, we are given the duty cycle. Duty cycle is 80%. T is 0.8, right? Okay. We're also given the voltage drop. Voltage drop. So I'll call this VD is 1.5, and this drop is when the chopper is on, right? 1.5 volts. We're also given the load resistor, which is 20 ohms. And then also given the frequency, 10 kilohertz. Okay. Now the question, we have to find what? The output DC voltage, and also have to find T on. Okay. Yes. So what do we do now? Okay. So since we're not told what kind of a chopper is this one, is not going to assume the first case, right? Okay. So I'm going to say, okay, DO is equal to VS times a diode cycle, right? Okay. And we know that diode cycle is simply equal to what? T on over what? Over T. Okay. T on over T. So I can go back and substitute here, right? So VO is equal to VS times T on over T. But wait, we are told that when the time is on, during the T on, there's voltage drop of 1.5 volts. So I have to subtract. This VS now have to be subtracted by VD. Okay, so that you have our new equation, V output will be equal to, so T on over T is simply duty cycle, remember that? Okay, so I can replace back the duty cycle, and we already know this guy here. This will be equal to VS minus, okay, so the source voltage it has to be reduced by VD. Don't forget that, right? Okay, and then now we can multiply by the duty cycle. This is T on over T, right? Are we together? There's a voltage drop there, so we have to consider it. Okay, there's a voltage drop there, so we have to consider it. Okay, now what will be the output voltage? So the output voltage will be equal to the difference between the voltage, the two voltages, which is 220 minus what? 1.5. The D is what? The D is 0.8. Make sure I convert it to what? Decimal. Don't use percentage here. Okay. So what's the output voltage? So what do you get when you compute that? Okay. So if I get my calculator here, I put everything, I'm getting about 1.74 or 174.8. Volts, right? Okay, now since we found this output DC voltage, we can now find the time T on, right? So T on, we can even use this formula now here, right? Instead of us using the duty cycle, we can use the formula there. So we can use the definition for duty cycle, okay? So you notice that if you make T on the substitute formula from this guy here, you're going to have T on is equal to VO over VS times what? Times T, total time period. So, oh, what is T? Okay, we haven't found T yet. So T is simply equal to 1 over frequency. So it's 10 kilohertz frequency, 1 over 10 times 10 to the power 3. So this guy becomes milli. So it's 1 over 10 milliseconds. So which is what? Is 0.1 milliseconds. Okay, so 0.1 milliseconds. That's the time period, right? So let's find time on, right? T on. VO is 174.8 divided by what? Divided by VS. Our VS is 220. times 0.1 millisecond. Okay. So how much is that? Let me just also put that in the calculator. So 174.8 over 220 times 0.1. So this is 0.079. And if you want to convert to micro, you can convert that to microsecond, okay, if you like. So it's about 80 microseconds. That's 9.4, so about 80 microseconds, I think. Is that the case? Yeah. If you want to multiply this guy by 1000, so 9 point something. So I'll just round it off to 80 microseconds. Okay, now that's the time when it's on, right? What else? That's all, I think. You can also find what time for doing what time period when it was off. You can also do that, right? Yeah. Just subtract from the total time period. So 0.1 milliseconds minus 0.079 milliseconds. You're going to find the time when it was off. It's 20%, right? Oh, and if you want, you can find 20% of 0.1. Because look, the duty cycle is 80%, right? So I mean the remaining 20% was off. So just multiply 20% by 0.1. Okay, you're going to find the time when it was off. So that's correspond to off time period 20%.